Hello everyone and welcome. My name is Annibale Panichella and together with Cynthia Liem we will present our paper entitled Oracle Issues in Machine Learning and Where to Find Them. Nowadays, machine learning has become a very hot topic in many domains, which also includes software engineering. For example, we use machine learning to try to automate software engineering tasks, but also we use software engineering methods to improve machine learning. For example, the reliability of the trained models. Among the different methods, software testing covers a very major role. As a software engineers, for example, we are interested in testing the machine learning component, the properties of the models, the workflow, and the usage to specific domains. Classical example, testing for self-driving cars. Over the years, the number of papers in the field is steadily increasing, and we also have dedicated workshops, conferences, and surveys that aim to provide an overview of the field from the software engineering perspective. Cynthia, but what do you think about this overall effort from the software engineering community?
Well, it's really interesting, because ever since we also started talking, what really struck me is that software engineering people and machine learning people have a rather different take on how to assess whether a system performs as intended. What I've seen as an outsider regarding software engineering is that if you build a system, you first settle on explicit requirements. The system is then being developed, and it's ultimately assessed through testing. Now, the testing procedure can be an independent procedure from development and requirements elicitation. It also may be conducted by a different party than the party that did the development or the requirements. This is different in machine learning. In general, we're often not as aware that we are building systems, we're rather thinking of optimizing to find mappings. In the most abstracted sense, we have input data X that behaves according to certain distributional properties. There is a ground truth output Y that we want to associate this X to. And then we seek to find these optimal mapping functions f of x that take x and map them to y. And for that we can choose many different types of models, for example neural networks. Now of course in practice we often apply this machine learning to real-world data and use cases. And there typically what we have is that our input data is data that would normally be judged and assessed by humans. We then have humans assessing lots of these exemplars for our y. And the idea of this intermediate model function is that we can find a mapping that mimics this as well as possible, such that we ultimately have a scalable automated procedure to expand this. Now then, we can definitely argue we are working on systems, but the requirements for them are very indirectly reflected in the data through the exemplars that we have in the dataset. And to make sure that this data is sufficiently diverse and comprehensive, we try to seek large datasets with many different exemplars that, as representatively as possible, represent these concepts we want to predict for. Now, if a model got trained, we also want to assess how well the resulting model system performs. And for that in machine learning, we would partition our data beforehand. A big data set is at least partitioned in a training and a testing split, and sometimes also an intermediate validation split. During the training, one only looks at training. But then, when the resulting model is to be evaluated, one would look at how it performs on the validation and/or the testing split. In other words, we're trying to see whether the patterns that are optimized for are generalizing. Now, unlike this situation in software engineering, this does mean there is an explicit dependency between the test cases we are looking at and the whole development procedure of the model. Actually, our data test cases that we evaluate with are coming from the same distribution and the same underlying source, which is the data set out of which we also got the samples for which we trained. In general, our validation and our testing splits are the gold standard oracles. The best thing a system can do is to perfectly perform on these validation and test splits. But we can ask legitimate questions on whether that truly makes for a perfect system. Now, these questions I hardly see asked. I don't see them asked much in the machine learning world. Neither have I seen a lot of discussion about this in the testing for machine learning literature. Very often, tacitly, we just assume that the data sets are fine, and especially if they're large, it should be fine in most of the cases. But what I've found is that existing machine learning datasets often actually are rather unreliable oracles. There may be big issues with them in the way they are labeled. Also in the way they are framed and in the way that the optimization happens in machine learning frameworks. They may work well in the context of the original tasks that they were used for, but they may actually be very problematic if we think of real-world, broader, more integrative applications that I think are also more of interest in the software engineering world.
But that's a huge problem. How can we find all these issues?
It is a huge problem, and it also is very non-trivial to solve. In that sense, it's very close to the test oracle problem that is well known in software engineering. We know what the system is supposed to do, but we're trying to figure out what it actually doesn't do well beyond what we know it's supposed to do. However, I think that the machine learning procedure, the framework, its framing, looking more closely at that in relation to what we want to achieve, will already get our understanding quite a bit further. And for that, I want to show an example from visual object recognition, which is one of the tasks in computer vision that boosted a lot of AI research. Now, in terms of visual object recognition, we start with an image that needs to be associated to a particular label corresponding to an object that's depicted in this image. And that is actually not a trivial procedure for a machine to process, because computers don't see images, they see matrices of pixel intensities. Now, if we especially speak of potential deep models, they will operate directly on this raw pixel data. So if we want for these models to batch process a lot of input, that input needs to be standardized. So what you often see in an object recognition pipeline is that first image dimensions get standardized. For example, a square crop is taken from the middle of the image. That effectively is a matrix with RGB, red, green and blue pixel intensities, and that goes into the model. Now, as the model is being trained, we had this label of the class annotation. That is mathematically depicted as a probability vector, with a probability of 1 for the class that was annotated and 0 for all the other potential classes that could be predicted for. The model in its training time is being optimized such that it tries to maximize the likelihood that the true class is being picked. Ultimately, it will output an estimated probability vector, y hat, for all the different object classes we have, with the estimated probabilities of each of these classes to occur. Again, we'd like for that to be as close as possible to the original annotation. Now, if we look at these predictions, we commonly actually don't do that so much in object recognition, because there you just rank these probabilities and you take the best performing one or the highest performing ones. But if you look at the distribution of the model class probabilities, you can actually infer more information we can consider to use that as well in testing. Say that we, for example, have 4 potential classes to recognize from: goldfish, beagle, volcano, and shower curtain. If I have a model that gets an image and it gives like 90% confidence that it actually sees a beagle, we can consider this model to be confident. At the same time, if we have a model that outputs class probabilities that all are around 0.25 with just a slight increase for the beagle, there still will be a beagle recognized, but that prediction was clearly not as clear-cut. Now, as I said, this confidence information is typically not being taken into account in current evaluation frameworks for objects, but it's useful. And one way to quantify these notions is through a classical formula from information theory, the Shannon entropy, which encodes how much information is on a noisy channel. And in our case, this channel would be our class probabilities. So on the left side, we have a low entropy case. There is not that much information because the only true information in there is that the beagle is the most confidently predicted class. On the right we have a high entropy situation. There is a lot of information in there. We cannot really tell for sure which of the classes are in there.
Hang on. The 4 labels are also not independent from a semantic point of view. Indeed, we can say that the beagle is closer to a goldfish more than to a volcano. The first 2 are both animals, the third one is not. So we have to consider semantic, and we do so for 2 reasons. First, because labels are words in natural language, and words are by definition not independent. We can use many words to express the same concept. Besides, words that are used in the same context, although different, are also somehow linked to one another. The second reason is that when we take a picture in real life, hardly contains only one object. Usually it does contain multiple objects, which means that we have to be open to the possibility that an image has multiple labels. To address the semantic challenge, we use WordNet. WordNet is a database of words for the English language, and for each word that is called synset, it provides the definition but also the semantic link to other words. We consider 3 different relationships: synonyms, so pair of labels that have the same meanings but are actually spelled and pronounced differently. Homonyms are labels that are spelled and pronounced the same but have completely different meanings. And finally, meronyms, classes of labels that are linked by a part of relation. For example, a wheel is also part of a car. So if you take a picture of the car, depending on the angle, may also contain actually the label, should contain the label for the wheel. So summarizing, I think, so we can consider these 2 aspects. The first one is about the distribution that we can obtain. The second one is about the semantic relation. This is from theoretical point of view. Cynthia, do you have in mind a real-world dataset that we can use to assess our 2 heuristics?
Yes, there is. ImageNet, the visual complement to WordNet. ImageNet collected lots of images from the internet, which were annotated with WordNet concepts in a crowdsourcing manner. Annibale, is there a bucket in this image?
Yes, I would say so.
Right, I'd say the same. This was the way in which the labels were acquired for many, many images. Out of the very large database that was constituted in that way, many datasets got subsampled that were still very large and used in many computer vision benchmark challenges. The most famous one was the ImageNet Large-Scale Visual Recognition Challenge of 2012. It involved a visual object recognition task with 1,000 image classes, which was very clearly won by deep convolutional neural networks, and that basically sparked the large interest in deep learning in vision. Nowadays, when new deep models are made, they are commonly benchmarked on ImageNet, which means that they are trained and evaluated on the same data splits that were used in this 2012 benchmark. Top 1 and top 5 accuracy is commonly being reported, and well-performing models, as soon as they got trained, are commonly also released to the broader public for use in transfer learning as a consequence. So what we did in our work is to take 4 such classical pre-released, pre-trained models, common architectures well known to be performing well on ImageNet. We ran them on all 50,000 images in the validation split of the ILS VRC 2012 data, and also applied the same pre-processing methods. And then we used our heuristics to surface potentially striking outliers. As for that, we currently were checking those outliers manually, but we could imagine that these heuristics can be used in more automated frameworks. And then some interesting examples we saw here. This was an image with the ground truth class NEPAD, for which none of our 4 models managed finding a NEPAD in its top 5, and overall showed very high entropy in the predictions. What turned out to be the case? The pre-processing. Commonly, the standardization was to take a square center crop out of the image, which in this particular case led to only a white square being offered to our models, and that was why they were confused. On the other end of the spectrum, in terms of low entropy, the image that had a bucket never had a bucket recognized for all the 4 models. Instead, the models were convinced with a probability of 1.0 that the class for this image should be baseball. And that is actually imaginable. This shows the issues with only having a single class label for an image. Then we also looked at common confusions in class predictions, and the striking one was that laptops often got predicted as notebooks, which actually are also WordNet synonyms. But when we look more closely at the class confidences, we see rather big differences. This is a prototypical image that has laptop as ground truth, but is classified by the models as a notebook. But if we see, it actually doesn't see notebooks and laptops as equivalent. It is much more confident that it sees a notebook than that it sees a laptop. That doesn't really match human perception. But is it a bug or a feature? Actually, it is a feature, because if we remember how these tasks were framed, with the ground truth class initially being a 1 and all others being a 0, clearly models get steered to mimic that, especially under maximum likelihood optimization. And by this criterion they are encouraged to really see different object classes as independent, and to really go for 1. As some further examples of what can happen there, also in terms of semantics, in WordNet we found some meronyms in these 1000 classes of this benchmark task. For example, stone walls, which are parts of castles. Now this is a castle image that convincingly got classified as a castle. However, the models really did not see any stone walls in there. And it could be imaginable if you look at what typical stone walls look like. They typically didn't include buildings around them, but really were focused on the walls. So as we see, this benchmark, even though the models trained on it managed to pick up salient visual features, definitely doesn't representatively show the world. Out of these 1000 classes, also more than 100 include subspecies of dogs. And that was because of this academic benchmark. People were interested in 2012 to see whether models could specialize and generalize. Then if you look at other classes in there, there is one red wine class, but no white wine. One Granny Smith, but no other apples. One carbonara, but no other pasta dishes. And that's for the carbonara. If you look at these images here, according to ImageNet, these two images are equivalent exemplars of the carbonara class. But if I show the top right image to an Italian... Oh goodness.
Che schifo, che schifo! Cioè, tu mi stai dicendo che questa hanno preso una ricetta che mia nonna ha fatto 40 anni fa e ci fanno a mettere tu cosa in go.
Alright. So is this a problem? Have the computer vision specialists done wrong? Well, not entirely. If you think of the tasks they tried to solve, they focused on object class prediction. And for that, all the framings we saw were fine. The errors are understandable, and other issues come with the modeling, but that modeling is justified. But if this model is to be integrated in a larger real-world application, we need to think more closely. I don't think you want a vision component like this that would really be steered to recognize a single object to go into a self-driving car. So let's be mindful. When we think of testing for machine learning, let's not really take those existing data sets for fully reliable oracles. There should be some awareness of what the models should be seeing and predicting given the use cases they're used for. And regarding that, I think the software engineering and software testing perspective can be very valuable, where testing is not necessarily already pre-established as the data gets required. And furthermore, I think we should collaborate together to see whether potential criteria, modeling, mathematical framing is actually also justified with respect to the tasks we are trying to solve. Thank you very much for your attention. Annibale and I will be happy to take any questions from your side.